Okay, good afternoon, everyone. Those who are new here, welcome to Taylor's, and those who are coming back from summer break, welcome back. I am Dr. Fatima, and I'll be teaching you discrete structures this semester. Okay, and let's just dive into what we have to do. First, I will start. For those who are new, I'll start with some important information that you need to know about where all the module-related resources and information will be available to you. And after that, we'll start with our today's lecture. So the main, let's go through this. Platform will be My Times. All the information will be uploaded over there, and you can access it through your student app, and also there is a desktop app. So I would suggest you to go to access this all the information through your desktop app as well from time to time, because sometimes some things you cannot really see them in your mobile app. Okay, so make sure to go through it through your laptop or iPad or any other device other than your phone. And there are the main sections. I'll just walk through those for you. First one will be the announcement sections. Any information related to the assessment date, or if there is a public holiday, replacement class for that, or any similar information, that will be posted over here and you will receive an email. Okay, otherwise, if you don't get it, but let's say there is a public holiday and I've posted the replacement class for that, but you cannot see it on your student app, just go log into your My Times and check, okay? And this will be your first section. And next you have module information, MI. Here you will find how this course is designed, what are the graded assessments that you have to attend or attempt to pass this course, and weekly agenda, rough weekly agenda, and the topics that you will cover, and also study resources, but study resources I will put them in another section separately as well. Okay, that will be your module information. Next will be lecture notes, weekly lecture notes. All the lecture notes starting from week 1 to week 14 will be uploaded by week 2 in this section, in the lecture notes section. Okay, and every week when I teach you, if there is anything that I add, the lecture will be updated weekly. But the main lecture notes, they will be uploaded, all of them, by next week. Okay. And next section will be your tutorials, because for this module, you will have two types of classes per week. One will be your lecture class, and second one will be your tutorial class. Okay? Every week, you have to attend two classes. Lecture class, today's class of 2 hours, and tutorial class 1 hour. Okay, so check your student app. You can find out which tutorial section you belong to. Okay, it will be, you'll have a code for that, TUT01 and then /0102 up to, I think 20 sections are there, so you can find out what is your section from your student app. Make sure that you check it out, you check the time, and you attend the correct class, okay? And in tutorials, usually we do the exercises about the topics that we cover in your lecture class. And there are 3 lecturers, one me, and then we have 2 other lecturers teaching this module who will be teaching you tutorials. One is, we have Dr. Salia and Dr. Ayu. So you will get to know them next week, okay? And please no talking. I don't want any talking in my class while I'm giving you the lecture or talking about anything. After the class, you are free to talk. Okay? No talking during the lecture. And then there will be, if we go through the MI, there are 3 module learning outcomes, known as MLO. The first MLO is test is mapped against that MLO. You can find out when we'll have the test, and we'll also post the test date on my times. But your test is mapped against MLO1. You can go through that in your MI document. Second MLO is your group project, group assignment is mapped against that. And you will have to work in groups of maximum 5 students. Okay, I will guide you about that next week. And then your final exam is mapped against third MLO. So these are 3 graded assessments that you have to pass this module. So you have to attempt all 3 of those. In each assessment, you have to get 40% marks to pass, but overall, to pass this module, you have to get 50%, okay? And you cannot skip any of these 3 assessments. Test carries 30% weightage, group project carries 30% weightage, and final exam carries 40% weightage, okay? Your final exam will be in week 15, 16. You will get the schedule for that. You will be notified when the time comes, okay? And yeah, that's all. That's the basic fundamental information that you need to know for now. And next, I'll go through what topics we will cover. We'll cover logic, and within logic, propositional logic, predicate logic. And then we will have proof, in which we will study direct proof techniques, disproof by a counterexample, proof by contradiction, and mathematical induction. Okay? And then we will have set theory. Within this topic, we'll have several subtopics like introduction. First, I'll introduce you to what sets are and the basic information about the set theory, and then functions and relations. Before that, Cartesian product and Venn diagrams, etc. And then you will have counting. We will study sum and product rule, inclusion, exclusion principle, pigeonhole principle, permutations, and then we'll have graph theory. It is divided into 2 main subtopics, your different types of graphs, and some rules and laws associated with those, and then some special types of graphs called trees. Okay, so these will be your 2 main subtopics in graph theory, and then a brief introduction to probability. Okay, so that will be what we'll roughly cover in this module. On weekly basis, we will go through related information in detail, but for now, let's go through your attendance. You will have to mark your attendance in the last 15 minutes. I'll generate the code. You will have to mark your attendance, and if for any reason you are unable to mark your attendance, there may be a problem in technical issues. Last semester we had that. You need to tell me during the class. After the class, no, I'll not accept your email or anything that you were unable to mark your attendance. Mark your attendance during the class. If you are unable to do so, come to me during the class, okay, on the spot. Clear cut, okay? And if you have to, if let's say you have anything and you cannot come to the class, apply for leave through your student app, okay? Online Campus Central portal, not the office, but the online Campus Central portal that you can access through your student app. Apply for leave and attach supporting document, okay? So that will be it related to your attendance. So I think that's all for now. So we will start with today's lecture. First lecture is about propositional logic. You can find it on my times. And if there is anything that I add here, I will update the lecture on weekly basis, all right? But in propositional logic, what we will cover is first what proposition is, and then what compound propositions are, then how can we form compound propositions. We use logical connectives. Just like in your mathematics, you have different operations, addition, subtraction, multiplication, division, and so on. Similarly, you have logical connectives over here to when you want to combine two or more propositions to form compound propositions. We will cover 4 main logical connectives that can be used to form compound propositions, and then what truth value is, truth table construction. This lecture and the next one is actually, this one is heavily dependent on truth table. You should know the rules, you should know the hierarchy. We will go through that one by one. How to draw the truth table, what are the rules related to or associated with different logical connectives in order to draw the truth table. And after that, we will have a logical equivalence. What logical equivalence is, how to find out whether the propositions, two given propositions, are logically equivalent to each other or not. And then we'll have special cases of compound propositions, first tautology and second contradiction. And then we have something called conditional statement, 3 different variants of those conditional statement. We will cover those. And lastly, what argument is and how to find out whether an argument is valid or invalid. Okay, that is what we will cover in this lecture. Let's start. So simply, if you look at what proposition is from English language point of view, we know that there are different types of statement. We have question, we have commands, we have propositions. So proposition is simply a statement about which you can determine that whether it is true or it is false. Okay, so that is what proposition is. What does it mean? That a proposition or a statement, these terms will be used interchangeably. Proposition, propositional statement, statement, statement variable, these are all relevant terms. So when you can say about a sentence that it's true or it's false, that is called as a proposition. Okay, and it can be true, it can be false, means it has 2 possible truth values. Okay, so this is important because we will use this concept to draw the truth table. Here we have some examples, very simple examples. 2 plus 2 equals 4. You can tell, it's true or false, right? You can determine that. So it's a proposition. Next one, 2 plus 2 equals 5. You can say whether it's true or false. It's false, right? You can determine that. So it's a proposition. It's a false statement or false proposition. Now, those who are taking data structures and algorithms and then or any other programming module, you know that we assign these statements or operations to a variable, right? So here also these statements, we will assign a variable in which we will store these statements. For the sake of uniformity, we will use P and Q variable if we have 2, okay? If we have 2 statements, we will use, like for the first one, P, and for the second one, Q. And if we have 3, maximum will be 3 statement variables or 3 propositions. So P, Q, and R. You can use any variable, but just to be like, for this lecture, we'll use, we'll stay constant, so P, Q, and R. All right? So let's say this is one proposition. We want to assign it to a variable. We can assign it to P variable and second one to Q. Okay, we'll look at it later as well. But anyway, that's what proposition is. There can be variables within the statement. Okay, this we will look at in your next lecture, predicate logic there. But for example, if an integer x is a multiple of 6, then x is even. This is also a type of proposition or a statement, and we call it conditional statement, okay? If and then. All right, if and then, so like it is known as conditional statement. Then there is a simple exercise for you. Sydney is the capital of Australia. Is it a proposition or a different type of statement? Yeah, yes. And then do tutorial 11 now. No, it's a command, right? So it's not a proposition. And today is Wednesday. Yes. X is a prime number. Some people who teach discrete structures, they say this is a proposition, some say it is not, because we don't have the value for x, okay? So, but in this lecture, we'll say that this is not a proposition. If we know that what the value of x is, then we can determine about it, it's true or false, then it will be a proposition, okay? But this is a bit ambiguous. For this lecture, we will consider it as false, okay? If we know the value of x or the variable, then yes, then we'll say that it's a proposition. 5 is equal to 2? Yes? Proposition, right? Because you can say that it's true or it's false about it, right? Okay. All right. Then this was what, this was about your proposition. Now, if we want to combine 2 or more propositions, we need to have some operations or some connectives. We will cover, in total, we will cover 5 logical connectives, out of which 4 will be specifically used to combine 2 or more propositions. The first one, negation, it is not necessarily used to form compound proposition. It is used to alter the truth value of a proposition or a statement. Next is conjunction. Then we have disjunction, implication or conditional. Then we have biconditional or equivalence. And in these connectives, we perform different operations. Let's look at it one by one. For negation, you need to know, what you need to know about this is, where is it? Wait, oh. Let me just switch. Okay. Is it visible? The slides, are they visible to you? Is it okay? Okay. Okay, so what you need to know is name of the logical connective, which is the negation, first thing. Second thing, which operation we will perform. Okay, for example, in this, we'll perform not operation. And third, the symbol for that. For negation, we have 2 different symbols. Either of these is fine. You can use any of these, okay? What we do is, for example, the number 2 is even. This is our original statement or proposition. I will either use statement or proposition, means the same thing, okay? And if we want to negate it, in English we can write it in different ways, but symbolically, for example, this statement, we assign it or we store it in variable p. Then if you want to negate it, we can write it symbolically like this, okay, or like this, okay. So this is your simple logical connective, and we don't necessarily use it to form compound propositions. Next one, yes, this is used for combining 2 or more propositions. Conjunction, the name of logical connective, first thing. Second thing, you need to know what operation we perform. We perform AND operation. Third thing, how do we write it symbolically, okay? So these 3 things, and we need to have at least 2 statements to perform conjunction, to have this conjunction, okay? And let's say, for example, we have one statement Number 2 is even, and then we have second statement. Number 3 is odd, stored in Q variable, and we want to combine these two using conjunction. How can we write it symbolically? Write its statement. This is called as statement variable. Okay, and then the symbol for conjunction and your next statement variable. So this is your conjunction, and this statement will have its truth value. It can either be true, it can be false, and second, it can either be true, it can be false. Now we will use this information later. We will look at that to draw the truth table, and then this conjunction will have its own truth values, combinations based on the combinations of these two statement variables. Okay, but basically what we do is in conjunction we perform AND operation. Okay, that is what the key information. Next logical connective is disjunction. This is your third one. What operation we perform in this one? Sorry. This is the first thing that you need to know. Second is OR operation. And third thing is how do we represent it symbolically. So let's say we have two statements stored in two statement variables, and we want to combine them using disjunction. How do we represent those? Like this. This is the symbol for your disjunction. Okay, and examples, we will look at these later. But this is your second logical connective for forming compound proposition. And then we have conditional or implication. Here we have this form. Okay, this is how we read it. If P then Q in English. And how do we show it symbolically? Single-headed arrow. Now here you need to know two more terms. For conditional statements and then next biconditional statements, you need to know two main terms. First is hypothesis. Let's look at it here. Is your conditional. First is hypothesis. I hope all of you know what hypothesis is. Inference. Okay. And then we have conclusion. These two terms. Now in conditional, how do you show it or how do you write it symbolically? Single-headed arrow. Okay. So remember, whatever is before the arrow, that will be your hypothesis. Whatever is after the arrow, that will be conclusion. Okay. And this you will need for your conditional and biconditional statements, because we'll have rules based on how we will word them out. We will be using these two terms, okay, when we draw the truth tables. Same is for your biconditional. This is the last logical connective. We represent it, or symbol is double-headed arrow. And again, whatever is before the arrow, this is your statement variable in which the statement or proposition is stored. And whatever is before the arrow, that will be your hypothesis. And whatever is after the arrow, that will be conclusion. Okay. So these are 4 logical connectives for compound propositions. In addition to, we have negation. Okay. So 5 in total. Now in English, we can read them in different ways. For conditional, we read it the main English statement is if P then Q, and we can also read it as Q if P, like if P is there, then Q will be there, and then whenever Q happens, whatever is stored within Q, whenever Q happens, like this will be necessary for P to happen. Like these things, you go through these, and then if you don't understand anything, just let me know. But basically what you need to know is from here, the extract is, this is what you need to know. If P, then Q. And what is P? This is your hypothesis. And what is Q? Conclusion. That is what you need to know. We'll study more about it when we are drawing the truth table. Okay. And these are simply different ways of writing the conditional statements in English. Biconditional, I have already covered that Before drawing the truth table, let's go through the hierarchy of logical connectives. Let's say we are given a compound proposition with more than one logical connective in one proposition. So, and we want to find out the truth value of that proposition. How, like in your mathematical statements, let's say we have addition, subtraction, multiplication, and division in one statement. Which one do we solve first? Similarly, over here, if we have more than one logical connective in a compound proposition, which one to solve first? Okay, so we have 3 levels. First, if there is negation in the statement, we will solve that first. Okay. The second is conjunction and disjunction. They are at the same level, but after the negation. If we have both conjunction and disjunction in one statement, and we have to solve it, we can solve either of these first, but after negation. Okay. So it is at level 2. Then we have conditional and biconditional. These we will solve at the end. We can solve any of these first if we have both of them in a single statement, but after solving conjunction, disjunction, and negation. Okay. But there is an exception. If there is parentheses in a compound proposition, we will solve that first, regardless of whatever logical connective we have. Okay. So first we will solve the bracket. Okay. Parentheses, and after that we will look at these this hierarchy of logical connectives. Okay, so 4 things you have: parentheses, then negation, then next will be conjunction and disjunction, lastly conditional and biconditional. Okay, so this is your hierarchy of logical connectives, and this will also be useful when you have to draw the truth tables for verification or for validation of arguments. Let's look at some examples. Let's say examples of how to convert the statements from simple English statements to the symbol form. So let's say, and also these questions, pay attention to the examples given in the lecture and in your tutorial exercises that you will start next week, because the pattern of question will be same in your test and final exam. Okay, if you have structured questions in your test, the pattern of questions will be similar. So let's say, let's look at this one. Write each of the following sentences symbolically. We are given 2 statements. They are stored in 2 variables. First statement variable is h, and second one is s. And you have to, now this information is given to you in the question. And after that, what you have to find out, based on the initial statements given to you in the question, there are some other conditional statements given to you that you have to write down symbolically. Okay. So for example, it is not hot, but it is sunny. Look at the question, what is given there. In the question, you are given it is hot, right? So what does it mean? In the answer, what you have to do? In the question, it is not hot. So yeah. First, you have to negate it. You need to know the statement variable. So for it is not hot, in the question, the statement variable is h, but you have to negate it. So write the symbol for that. And then, but it is sunny. Then you have to see that how they are logically connected. So which logical connective you will use? And, okay, conjunction. So symbol for that. And then it is sunny, so that is simple. We have it over here in the question. Write down the statement variable for that. So this is how you translate from English statements to symbolic form. Okay. Next one. It is neither hot nor sunny means both of these things are there. So it means you will perform AND operation, but you will negate both of them. Okay. So this is how we do that. We are using conjunction because both of these we need to include in the compound proposition. Clear? Is it clear? Okay. Then another type of question that we can have is, This is also similar, just that you can, instead of simple statements, you have some mathematical operations, some mathematical expressions, okay? So let's say, let's look at, you have some mathematical operation stored in 3 statement variables. Here you have now this information is given to you in the question, and then some statements are given to you, and you have to utilize this information to write, to translate that statement into its symbol form. Okay, so this first one, x is less than or equal to 3. Break it down into what do you have in order to find out what is stored and which symbol you have to use. What does it mean? That x is either less than 3 or it is equal to 3. Now you have broken it down, and then you have the information given in the question. Simply write down the symbol. You have the logical connective, just write down the symbol for that. Okay. So x is less than 3, you are given here, it is stored in q variable. Okay. And from when you dissected the question, from there you got to know that we are performing OR operation. Okay. X is less than 3 or it is equal to 3. That is why you, that is from where you know that it is the OR operation. Write down the symbol for that. Symbol we know it is V. And then x is equal to 3. Look at the question where it is stored. X is equal to 3 is stored in our statement variable. Okay. So simple translation step by step. Okay. Next one is, can anybody try this one? Yeah, yes. Yeah, yes. Because it yes. So when you read this expression, it tells you what logical connective you have to use, because it tells you what operation you have to perform, right? So for example, here it was x. If you read it in English language, x is less than 3 or it is equal to 3, it tells you what operation you have to perform. Similarly over here, correct? X is greater than 0 and it is less than 3, so you know and operation you have to perform. You just have to know the symbol for that to write it down symbolically. Okay. And same applies over here. This can be a bit complicated. It's easy, but still x is greater than 0 and it is either less than 3 or equal to 3. So you have both AND operation and you have OR operation. Okay. So that is why I said this one, first example was pretty easy, but second one you can have nested operations in your in the questions given to you. Okay, but hints you will get from the question. Most of the time, this is I'm telling you generally, most of the times half of the answer you can get from the question. So learn to read and interpret the question carefully. This applies to any topic, any lecture. Okay, so read the question carefully, dissect it, break it down into pieces, and you will get, most of the times you will get half of your answer from the question. Okay. So that is about translating propositions from English to in their symbolic form. Next, we will look at how to draw the truth tables for each logical connective. For negation, it's pretty easy. Let's say the original statement variable is, okay, first let's look at, let's say this is our statement, okay, and we know that it can either be true or it can be false, so we will write both of those in your table. And for negation, if the original statement is true, in its negation it will become false. Pretty intuitive. And if it is false, then its negation will be true. Okay, so this is for when you have one statement or one statement variable. Okay, And then after this, we will have conjunction, truth tables for conjunction, truth table for disjunction, truth table for conditional statements, and for biconditional statements. Each of them have some rules to write down the truth values for these. Okay, so maximum we will cover up to 3 variables because after that it becomes a bit difficult to draw the truth table, and then because we will have more, we will have compound propositions, so it will be very complex to draw. So for this lecture, maximum variables that we will have in one compound propositions will be 3, unique variables will be 3. Okay, and a simple formula to find out how many rows in total you need to have in your truth table. This is your simple formula. What does n represent? Number of unique statement variables. So let's say a question is given to you. It could be question related to logical equivalence, it could be related to argument or whatever, but you have to, let's say you're asked to draw the truth table for any purpose, and you want to verify, you want to check whether your truth table is correct or not. How many total rows you need to have? Use this formula. N will be equal to the number of unique variables that are given to you in the question. Okay, let's say you have 2 unique variables. It means this is equal to 2. So how many total rows you need to have? 4 for your truth table to be complete. This is easy. This seems easy, but I have seen students missing 2 or more rows when they have 3 variables, especially in those cases. Okay. So this is just for you to verify in your exam. If you have to draw a truth table to verify whether your truth table is complete or not. Okay. For conjunction and disjunction, those who have studied logical gates, you know that how do we draw the truth tables, how do we perform AND operation. But there is just one rule for each of these. For conjunction, in let's say minimum you need to have 2 statements, right? You need to have 2 unique variables. So we have this is your truth table with 2 variables, and what I tell my students is to draw the truth table in order, in sequence, especially when you have compound propositions with more than one logical connective. So let's go through it one by one. Let's say these are your 2 unique variables. Possible truth value for, because we need to have 4 rows, so we will write down all the possible combinations. So either both the statements could be true, or the first statement could be true, second could be false, first statement could be false, second true, or both of these could be false. So these are all the possible combinations for 2 statements. Okay, when we have 2 statements. Now let's find out the truth value for conjunction. So what do we do in conjunction? What operation do we perform in conjunction? AND, yeah. So this one, and we'll also do the disjunction over here. So for conjunction, it's easy. Only in the case where both the statements are true will their conjunction be true. In all other cases, it will be false. If one of the statements is false, or if both of these are false, this is simple rule for conjunction. Okay, one rule only. Only in the case where both the statements are true will their conjunction be true. In all other cases, it will be false. Now this is for conjunction. For disjunction, how do we represent it? Upside down. And then we have, this is disjunction. What operation do we perform in disjunction? Yeah, or. So in that, only in the case where both the statements are false will their disjunction be false. In all other cases, it will be true. If one of the statements is true, or if both of the statements are true, the disjunction will be true. So opposite, conjunction, disjunction, they have opposite rules. Okay, this is easy. Now we will look at conditional and biconditional. For conditional and biconditional, they share one rule, and there is additional rule which is different for each of these. Let's look at conditional first. What does it mean? How do we read it? How do we read a conditional statement? Yeah. Any statement variable, it could be any variable, but here we are using P and Q. So if P, yeah, okay, symbolically, single-headed arrow, and okay. So again, we have two unique variables. Let's write down their truth values. Now here you need to, you will refer to the hypothesis and conclusion, these two terms, okay? They're conditional. So first rule is that when both the statements have identical truth values, in that case, their conditional will be true. Doesn't matter, false, false, true, true. In both the cases, when both the statements have identical truth values, their conditional will be, the truth value for their conditional will be true, okay? So, true, true, false, false, their conditional, true. Now, when the hypothesis is true, this is your hypothesis, why? Because that is the one that we have before the arrow, that is your hypothesis. So, when the hypothesis is true, but the conclusion is false, in that case, the truth value for their conditional will be false, okay? Because if the hypothesis is true, you need to reach the conclusion that is also true. Let's say it is raining, but the streets are dry. Is it possible? No, right? So, if you assign that it is raining, this statement to your hypothesis, the first variable, and the streets are dry, to the conclusion doesn't make sense, right? That is why their conditional is false, okay? So just you can take any similar example and keep that in mind to write down the truth value for conditional if you have it in exam, because we will use all of these in your in logical equivalence, in validity of argument, okay? And next one is when the hypothesis is false but the conclusion is true. In that case, its conditional will be true. It's not raining, but the streets, you know, they have water or you can snow, whatever, because there could be another reason. Maybe someone watered their plants, because of that the streets are wet, okay? So there could be any other factor because of which the conclusion is true, okay? That is why the truth value for the conditional in this case will be true. Understand? Is it clear? Clear? Yes? No? Okay. If you're not clear, let me know. I'll repeat it for you. But this is a bit tricky. Just remember the example of it is raining, or simply remember that, remember one of these. If you remember one of these, you will remember the other one. One of them is false, one of them is true. So it makes sense to remember this one, but it depends on you how you want to memorize. But when the hypothesis is true but the conclusion is false, it doesn't make sense logically. Remember, we are studying logic. It doesn't make sense logically. So that is why the truth value for conditional is false. And if you have like alternating truth values in the next one, then it will be the truth value of the conditional will be true. Why? Because there could be another reason because of which the conclusion has true as its truth value, okay? So these are the three, actually there are three rules for conditional, okay? So, and you write down the truth values by referring to the two terms, hypothesis and conclusion, okay? So this is for conditional statement. This is how you draw the truth table for conditional. If you are not clear, let me know. I'll repeat it now. You can raise your hand. You can simply let me know. Yeah, yes. Sorry? Yeah, yes. In tutorial, actually, there are some examples that are there in your tutorial. So in your tutorial classes, I will give you more examples, okay? So yeah. In tutorials, you will have exercises related to these. So for lecture, I will at most give you 1 or 2 examples for each topic because we have to cover, okay? And in your tutorial, you will have more examples. You will have examples for different concepts that we cover. And your tutorial lecturer will explain to you each different example questions, like 1, 2 questions for each different type of question, and then you will be given more to practice on your own, okay? But if you have any question, you can, if you still don't understand, you can ask in your tutorials, okay? Next, we have biconditional. Biconditional is easy. First rule is same. We sometimes abbreviate it to I and double F. It means if and only if. And how do we read it? If and only if P then Q. Okay, so it is more restrictive. And this is how we represent it symbolically. First rule is same. First rule is same as conditional, means if you have identical truth values for the hypothesis and for the conclusion, in that case, the truth value for biconditional will be true. And in biconditional, just remember that you cannot have different truth values for the 2 statement variables. So here you see different truth values. One is true, one is false. You cannot have that in biconditional. Okay, so you have if and only if P. If and only if P is true, then Q is true, and vice versa. It's like, let's look at it in the form of conjunction. This is how you can read the biconditional. Okay, so both of them need to be true. Both of them need to have same truth value for the biconditional to be true. In other cases, it will be false when there are alternating truth values. Okay, so that is how biconditional work. It is more restrictive as compared to conditional statement. Is it clear? Clear? Okay. All right. So this is all about your truth values and truth tables. Next, we will look at, this is what I explained to you, that when you have to find out the truth value for a given compound proposition where you have more than one logical connective, how do you translate and how do you use hierarchy of the logical connectives to translate, to solve this expression given to you or the proposition given to you, and all the other information, the truth values and everything that is given to you in the question, and then you translate it step by step, write down the truth values, and then apply the rule, apply the hierarchy, and then find out the truth value for this whole compound proposition. Let's look at one example. Okay. So this is the compound proposition for which you have to find out the truth value. You have to find out its truth value, and you are given the truth values for each unique variable in the question. I suppose it's true, false, and true. So P is true given in the question, Q is false, and R is true. So this is your information from the question, and then this compound proposition is given to you, and you have to find out the truth value for this. So the first step is write down truth values. Okay. So in the question, P is true, write down the logical connective. Then Q is false, write down its truth value. Then copy the logical connective as it is, and then the truth value for R given to you in the question. Now here you have to look at the hierarchy. You have to refer to the hierarchy, which one to solve first. So at first level, what do we have? Second we have this, and third we have conditional and biconditional. So this one is simple. Negation we have, yes. So what will be the negation of this? Yeah. And then which one will we solve first? Either of these. We can solve either of these because both of these are at the same level after negation. Okay, so it doesn't matter. True and false is, and then you are left with false or false, right? So that is false. Okay, so this one is easy, but let's say you have more logical connectives in a given statement. You will refer to your hierarchy to find out the truth value for a given compound proposition. It could be more complex than this. This one is easy. Okay, that is why you have to remember the hierarchy of logical connectives to find out the truth value for a given compound proposition. Clear? Understand? Yes? No? Yeah, yes. This one? Okay, let's look at another example, okay, because we have it over here. So we will look at this one, all right? Okay, let's say this compound proposition is given to us and we have to find out the truth value for that. Okay, and from the question we know what is the truth value of each individual statement. So in the question, P is true, Q is false, and R is true. Okay, here in the question, this one, P is true, Q is false, and R is true. Okay, and then we have to find out the truth value of this compound proposition. So first write down truth value for each of these. P is true, then we have conditional, Q is false, then we have conjunction, and then Q is false and R is true. Now after this, after writing the truth values, refer to the hierarchy. Okay, which logical connective to solve first? Yeah. So first we will solve brackets. Okay. Before anything, if we have brackets, we will solve the brackets first. We can solve any of these brackets first, doesn't matter. Okay. So this hierarchy is applicable in the, you can say that this, before that you have brackets. This is, this is how you can remember. So what will be the truth value for this? Now here you have conditional, you have hypothesis, you have conclusion. In the case where hypothesis is true but the conclusion is false, what will be the truth value of this conditional? False, yeah. Then you have conjunction, and then when the hypothesis is false but the conclusion is true, true. Okay, and then what is the conjunction of false and true? What is the truth value for this conjunction? False. Okay, so step by step. Clear? Is it clear? Okay. Okay. We have over here one more example. Let's go through this as well. Okay. Now, this is the third example that we have in the slides. Now here P is true, we have conjunction, R is true, then we have biconditional, then we have Q which is false, and we have a disjunction, and then R is true. Now which one will we solve first? Biconditional will be at the end. Conditional and biconditional will be at the end. Okay. So we will have, do we have negation, sorry, parentheses first, next negation, next conjunction and disjunction, lastly conditional and biconditional. Okay. So here we don't have any negation. So we have, then we have conjunction, disjunction. We can solve either of these first, or we can solve them at the same time. So true and true is, yeah, then we have biconditional, false or true is, yeah, and then biconditional of when the hypothesis is true and the conclusion is true, it is true. Okay, clear? Okay. And also from test and exam point of view, sometimes questions are very easy. You can get the answer without, like, you can do mental math and write down the answer. But the thing is that you are at university level, so here it's not only that you have to write down the answer, you have to give the answer. You have to show the steps. Important steps you have to show. For example, over here, I know that you can do mental math if you practice, and you can straight away write down its truth value, but no, you need to show at least these two steps, okay? Because usually, here in discrete structures, we have marks assigned to important steps, main steps, but they will be taught to you, okay? They will be taught to you during the class. For example, when you study mathematical induction, you will have two main steps. Each of them will have their own marks. So you will have to show those important steps to get full marks. Otherwise, maybe let's say you have a 5-mark question, only 2 marks are assigned to the correct answer. So you will get, if you don't show the steps, you will be given 2 marks only, okay? Clear? Next, we have logical equivalence. I will first go through what does it mean. What logical equivalence is? 2 statement forms are called logically equivalent. Statement form, simply, it means your propositions or compound propositions or statements. So same thing. 2 statement forms are called logically equivalent if and only if they have identical truth values for each possible substitution of statement variables. What does it mean? First, let's look at how do you represent logical equivalence. Let's say you have one proposition form or a statement form, and you have second statement form. You want to find out whether they are logically equivalent to each other or not. How will you represent? This symbol with 3 perpendicular lines will be used. Now, if this is true, this whole expression is true, how will you read it? P is logically equivalent to Q. Okay? When this is true, you will find that out by drawing the truth table for the statement given to you. So you will draw the truth table. First step will be you will find out how many unique variables you have in both of the statements that are given to you. That will be your first step. Second step will be you will draw the truth table based on that. Let's say you have 2 unique variables in the question. So, you need to have 4 rows to draw the complete truth table. You will draw that. You will use the rules, conjunction, disjunction, conditional, biconditional. Okay? So you will utilize those to draw your truth table. Then you will look at the columns for your first statement and second statement, for which you have to find out whether they are logically equivalent to each other or not. And for this logical equivalence to be true, all of the rows in these 2 columns must have identical truth values, all of them. Okay? Even if one of them have different truth values, it will not be, these 2 statements will not be logically equivalent. This is the rule. Okay? Let's look at it through an example. We will refer to one example that we in your conditional statement, you would see this rectangle, this one. Here, because we hadn't covered logical equivalence at that time, so I just ignored it. So we will look at this example now, okay? This means, how do we read it? That this conditional statement, P and Q, is logically equivalent to the disjunction of P and Q, where P is negated, okay? So this is the explanation of this statement. You have one proposition, and then you have second proposition, and in between these you have the symbol of equivalence. This is actually a rule. This is true. This is a law. Okay, so we can verify it by drawing the truth table and find showing that this is actually true, means these two statements are actually logically equivalent to each other. Okay, so we will take this example. There are two other examples also given to you in the slides. You can also refer to those. Let's first look at this one. Now let's say in a question you are asked to, there could be two types of questions. You would be given two compound propositions, and you have to find out whether they are logically equivalent to each other or not. What method you will use? There are mainly two methods. One is by constructing or by drawing the truth table. Second is by using the logical equivalence theorem. We will focus more on truth table, by finding out by drawing the truth table. Okay. So what logical equivalence is? The first step is, when you look at the question, what is the first step? You have to find out how many unique variables you have. Okay, that will be your first step in solving this question. Variables or variable statements or statement forms, anything, it's the same. Propositions, same thing. Okay, so look at overall how many unique variables you have. How many? 2, P and Q. Okay. So what does it mean? That in your table you need to have 4 rows for the table to be complete. So let's write down the truth values, all the combinations. Now you can write down the truth values of these compound propositions in any order, but I suggest to go to refer to the hierarchy of logical connectives, and in that order write down the truth values, because that is an easy way, and you will not miss writing down the truth values for any of the logical connectives that you have in your compound propositions, but it's up to you. Okay. Let's, if we refer to, let's look at the, by referring to the hierarchy. So based on that, first we have negation, right? So check whether you have any individual statements that are negated. Do we have? Yes, this one, right? So write down the truth values for that. Refer to this variable and just negate. True, negation will be false. Again, false. False will be true, and this will be true. Now, we don't have any other negation, so what is the next logical connective? Conjunction and disjunction. So check if you have any conjunction or any disjunction in any of these compound propositions. Do we have? Yeah, we have over here. So write the truth values for that first. So you see, you already have the truth values for negation, so you can simply refer to negated P and then Q and write down the truth values for their disjunction. Disjunction mean OR. So you will refer to this column and this column to write down the truth value for the disjunction. True or false is? True or false is? Yeah. Next. Yeah, next. Next. Yeah. Done with that, we don't have any conjunction. So next, at next level, lastly, we have conditional. So remember the rules. and then write down the truth values for conditional. Which columns we will refer to? These two. Okay. So true, true is, true, false is, false, true is, false, false is, true. True, true. Who said false? True. Identical values, conditional will be true. Okay. Now you have complete truth table with all the possible truth values for all different logical connectives. Now to find out the logical equivalence, what you have to do is you have to focus on the columns for these two. Okay. So where do we have? This is our first one and this is second. These are the two compound propositions for which we have to find out whether they are logically equivalent to each other or not. Look at their truth values in each row. All of them need to be identical. So true, true, false, false, identical, yes. True, true, identical, yes. True, true, identical, yes. So all of these are identical. That is why we can say that this is logic. This compound proposition is, this conditional statement is logically equivalent to this. Okay. So this is how we find out or we verify. Okay. Now one type of question could be that you have to find out whether the compound propositions are logically equivalent to each other or not. And second one could be that you are told in the question that they are logically equivalent, but you have to show it. Okay. You have to prove it or you have to verify. So, but method will be same. You will first step will be you will find out how many unique variables you have. Second step will be based on that you will have those number of rows and you will write down. And third step will be you will refer to your hierarchy, but it's not necessary, not compulsory. You can write down in any order. But a neat way to draw the truth table is that refer to hierarchy and check. If there is negation, write down truth value for that. If there is conjunction, disjunction, next write down truth value for that. Next, if there is conditional by conditional, write down truth value for that. Lastly, you will refer to the columns for the compound propositions that are of concern to you or that you are asked in the question to find out logical equivalence of. Okay. And for that, over there, what you will focus on, both of those columns, I mean the columns for the compound propositions need to have identical truth values in each of the row. Rule is in each of the row they should have identical truth values. Even let's say this was, for example, it was not true, true, it was true, false. Okay, but all other were identical. Still, will these be logically equivalent? No, right? So even if even one row, even in one row you cannot have alternating truth values. Okay, so that is one rule for logical equivalence to be present in the two compound propositions. Clear? Is it clear? Any questions? Yes? No? Clear? Okay. Okay, if you still have any questions, I have, you can ask me for consultation also, weekly or bi-weekly, but 2 days before the date that you want to have consultation on, you can email me and I can give you some time for that. All right. Next, 2 more examples are given to you. One is an example of when the statements are logically equivalent, and second example is when the statements are not logically equivalent. So you have one example each for both cases, and then this one I solved for this one, for conditional statement, okay? And this is a proven one. So you simply have to verify it by drawing the truth table. That is what I did in the example. Then we have 2 laws. Okay, we have 2 laws, De Morgan's laws, in terms of and or. okay, which laws of logical equivalence. The first one is that the negation of an AND statement is logically equivalent to its OR statement where each individual component or statement is negated. This is first law for AND, okay? Second one is, if you remember this one, you will know the other one automatically. First one is for AND operation, and second one is for OR AND statement, and second one is for OR. For AND, it is that if you know how to read it, you will be able to translate it intuitively. Let's look at that. So first one is negation of an AND statement is logically equivalent to its disjunction or an OR statement where each individual statement is negated. So you will need a little bit of practice to, when you are reading it, like in your mind, you can translate it. Okay, this is the first law, De Morgan's law for AND statement. Second one is negation of an OR statement or negation of a disjunction is logically equivalent to the conjunction where each individual component, by that we mean the statement, proposition, okay, which is like each individual statement is negated. So these are two laws. Usually we use these laws to find out the negation for given English statements. Okay, so we have some examples over here. But more important is that you should know how to draw the truth table to find out or to verify whether the compound propositions are logically equivalent to each other or not. And here I told you about the second type of question where you have to verify a given law. So here we have an example for that. This is this truth table. It verifies this De Morgan's law. Okay, De Morgan's law for OR statement or for disjunction. And this can be your practice, that this was for OR statement, and the second law we covered is for AND. So you can draw the truth table for that and verify, okay, verify the De Morgan's law of conjunction, okay, logical equivalence for conjunction. You can try that out on your own. And this will always be true because this is an established law. That is why if you see over here, the first compound proposition, the column for that is here. Second one is, column for that is here. You see, all of these are identical. So this is logically equivalent. That is why you have this law. If you would have, if you had alternating truth values, it would not be true, so it would not be a law. Okay. This is for your practice, and also during your tutorial class, we will discuss more about that. Let's just quickly go through it. For example, let's look at first one. Write negation for each of the following statements. You have to use De Morgan's law. First statement given to you is John is 6 feet tall and he weighs at least 60 kg. So you use De Morgan's law to find out its negation. In the negation, what did we see that how we negate it? If in the original statement you are given an AND operation, in its negation we convert it to OR. Okay? And if there is any neither nor not in the original statement, we remove that from the negation. If we don't have any negation in the original statement, we just add not, or you can use any English sentence, just that it will be opposite of what is given to you in the question. Okay. For example, John is 6 feet tall. In its negation, it will be John is not 6 feet tall. Easy. And you have AND operation over here. You will convert it to OR in its negation. And he weighs at least 60 kg. So you will write down the opposite of that. Okay. So these keywords, you will look at the keywords and simply change them to. Main thing is that for the logical connective, that clause or that word, you will change that to not, and you will change it to or you will change it to AND. Okay. So that is a simple way to find out the negations of given statements. And actually, they are pretty easy when you look at it from the perspective of simple English statements, just that we are looking at the De Morgan's law and seeing how De Morgan's law is being applied to find out the negation, okay? Let's take a 5-minute break over here. We'll resume at 3:30. Okay, let's resume. To recap, we have covered what proposition is, what compound proposition is, how to form compound propositions, logical connectives, 5 logical connectives in total. Out of those, 4 are used to combine the propositions to form compound propositions. Then truth tables, rules associated with each logical connective, and then logical equivalence. What is the rule when two compound propositions are logically equivalent? How to show, how to find out, and how to verify, okay, using the truth table. Next, we will look at 2 special cases of compound propositions. There are 3, but we will focus on 2 of them with examples. So first one is tautology, and second one is contradiction. Simply, the keyword for tautology is, let's say a statement is assigned to be or is a case of tautology. What does that mean? That it will only have true as its truth value. It cannot be false, regardless of other possible logic statements present in a proposition. Okay, there could be more than one propositions in statements in a compound proposition, right? We have at least 2 statements. So in those, if we have a case of tautology, that will always have true as its truth value. Okay. In case of contradiction, it is opposite. If there is a case of contradiction in a proposition, it means that it will always have false as its truth value. It will not be true in any case. So let's look at it through examples. Again, you can have two different types of questions here also. First type is over here. Show that the statement form P or not P is a tautology and the statement form P and not P is a contradiction. So here you have to show that these two statements are cases of tautology and contradiction respectively. So what you do is, same thing, you first find out, you have to show by drawing the truth table. First thing is, what is the first step in drawing the truth table? How many unique variables we have? Unique variables, like statement variables. One, P, only P. It's just that it is negated, but it's not a unique variable. Okay? This original statement, this is negated. It's not like a different statement. Okay? So we have one variable. It means this can either be true or it can be false. So this is P, and then its negation will be, because negation we have over here, so its negation will be, yeah. So that is what we have over here. I will not write that this down again. But after that we have, let me just erase this. After that we have truth value for its disjunction. So true or false is true, false or true is true. So this is what you have to show. Show that the disjunction of a variable and its a statement and its negation is a case of tautology. You showed it because regardless of what the truth values were in the statement and its negation, the truth value of its disjunction is always true. So this is a case of tautology. Okay, always you have true. And the second part of question was that you have to show that a statement, when you take its conjunction with, you take the conjunction or you perform AND operation with its negation, you have to show that this will be a case of contradiction. What does it mean? That the truth value of the disjunction will always be false, regardless of what the truth value of the statement and its negation is. Okay? So true and false is false, false and true is false. So in both cases, it is false. In all given cases, all possible cases, it is false, right? So we know from the concept of contradiction that regardless of the truth values in the statements, if a compound proposition is given to us and we have to show whether it is a case of whatever tautology or contradiction, we have to, let's say it's contradiction, it will always be false. Tautology, it will always be true. That is what we have shown over here. Understand? Clear? So simple is tautology, always true. Contradiction, always false. Okay? Regardless of whatever we have over here. Clear? Okay. This is one type of question. Second is that in the question, you are given a statement variable or you are given a proposition that is a case of tautology. Okay? So, for example, if T is a tautology, and then you will have to draw the truth table and find out whether two compound propositions are logically equivalent to each other or not. So, for example, if T is this is the question, if T is a tautology and C is a contradiction, show that P and T is logically equivalent to P. So, this first question. Second is P and C is logically equivalent to C. Now here you know that you have a case of tautology and you have a case of contradiction. Okay, what does it mean? Usually in your your normal statements, how many truth values are possible? Two, true or false. They could either be true or they could be false. But in tautology, how many truth values are possible? One, only true. So here, for this statement, you will write down true as its truth value. It cannot be false. That is why you have two unique variables, but you have only two rows. You know, why Why is that the case? Yeah, because for the tautology, only one value is possible. So only 2 combinations are possible. Okay, that is why you have 2 rows. And same applies to contradiction, because this cannot be true. That is why only possible combinations are these 2. Okay. So after that, after you have written down the truth values, P is the normal statement, so it can be true, it can be false. And T is the tautology, so it will be true in all cases. And then you are given a conjunction, because that is what's present in the question. Write down the truth value for that. We know P and like and operation, so true and true is true, false and true is false. Okay. And after that, for the first part, for first question, you have to find out whether P and T and P are logically equivalent to each other or not. So you will look at these 2 columns, see if in both cases they have identical truth values. Yes, true and true, identical. False and false, identical, right? So first one is, yes, it is logically equivalent because they have identical truth values. Clear? Now second part is where you have the case of contradiction. Now again over there you have 2 unique variables. You have P and then you have C. So P is here, and then for contradiction the possible truth value is only 1, which is false. And then you have a conjunction. You will write down its truth value. You will take the conjunction of P and C, means this column and this column. So true and false is false, false and false is false. Next step is, after writing down the truth value for the conjunction, what is the next step? Yes, what is the next step? After writing down the truth values for each of these, what will be the next step? Which columns we will focus on? For this one and this one. So they have identical values. Yeah, in the first row, yes. In the second row, yes. So these are logically equivalent to each other. So 2 different types of questions. One, you have to show, you have to verify that what is given to you is a case of tautology or is a case of contradiction. Second is, you are given a case of tautology, you are given a case of contradiction. You have to draw the truth table and find out logical equivalence. Okay? Clear? Is it clear? Okay. Next we have some laws. We use these, another way to find out logical equivalence is by using these laws, but we will focus more on using the truth table to answer the questions, okay, instead of applying these laws. But you should know these, you should know how to read these, what do they mean. This is, you have, I suppose you have studied your mathematics, so in algebra, right? There you have some properties, some laws, commutative laws, associative laws, distributive laws, right? So a plus b is equal to b plus a into b is equal to b into a, and then associative, I guess, or distributive, one of these. You have a plus b and then you have brackets, something like that. So they are similar. You have commutative law, you have associative law, distributive law in 2 contexts. One in and context, and second or. Okay, so at least know these. These are the laws, know these laws, but we will not really apply them to find out the logical equivalence. Not many like complex questions, no. But you may be, I might give you, if let's say this lecture is included in your test or exam, I might give you, let's say this expression to find out or to verify that these 2 statements are logically equivalent using the truth table. Okay, so usually for this, if we have to draw the truth tables for the laws, we are not finding out, we are actually verifying or proving, okay, because they are already established laws. Okay, so Next main topic is, before we wrap up, it is, we talked about conditional statements and 3 variants of conditional statements. So this will be our last topic for today. There are 3 variants of conditional statements. What can anybody tell me? A simple like conditional statement, how do we read if we have 2 statement variables? How can we have a conditional statement for these 2? Yeah, and symbolically? Yeah. So for this, we have 3 variants. Okay. First one is inverse. This is our conditional statement. Second one is converse. Third one is contrapositive. How can we find out inverse, converse, and contrapositive for a given conditional statement? In the inverse, we simply negate the hypothesis and negate the conclusion. Okay? In converse, how can we find out the converse for a given conditional statement? We swap the places of hypothesis and conclusion. So hypothesis becomes conclusion, conclusion becomes hypothesis, whatever is there. Okay. Sometimes, it could be, the statement could be like this. Okay. So be careful. Okay. To write down, just like know how to do that. Okay. For inverse, negate the hypothesis and conclusion. For converse, change their places. Hypothesis becomes conclusion, conclusion becomes hypothesis. For contrapositive, we do both of these things. We swap the places and we negate. Okay? Hypothesis becomes conclusion, conclusion becomes hypothesis, and we negate both of them. Clear? That is why I wrote in order, so it's easy. Inverse, negation, converse, swap the places of hypothesis and conclusion. Contrapositive, do both of these. Okay? Clear? These are 3 different variants of conditional statement. All right? And we can also find out inverse, converse, and contrapositive of a given conditional statement in informal form, which is your English statement. Okay? That we will look at in your next class or in your tutorial class. We can also show it through by drawing the truth table. And also, if you draw the truth table, let's say this is your conditional statement and you draw the truth table for that, and then write down the truth values for each of the variant, inverse, converse, and contrapositive, you will see that the conditional statement and its contrapositive will be logically equivalent. Okay, if you see look at their truth values. So these 2, conditional statement is logically equivalent to, to its contrapositive. Let me just write it down over here. Okay. So when we observe the truth table, we will see that we will find this out. Okay. Conditional statement and contrapositive, they are logically equivalent. So we'll stop over here and let's mark the attendance, and remaining we will cover in next lecture. So for marking your attendance, those who don't know how to mark the attendance, please ask your friends. They will tell you from the app. Here is the code. You have to enter this code to mark the attendance. And remember, I'll not accept any excuse after the class. If you are unable to mark, come to me now. Also, main mode of communication will be Teams. Okay, Teams, for each tutorial section, you have a group on Teams, and also you can text individually on Teams. So main mode of, please main mode of communication will be Microsoft Teams, okay? Also make sure that you check which tutorial section you belong to. Look at your student app over there, you will be able to find out. You will see something like this. Wait, 1 minute please, give me 2 minutes, please. You will see something like this on your tutorial, on your student app. 01 or 02, 03 or up to I think 20. So check in your student app which tutorial section you belong to. Every week you will have your lecture class, you will have one tutorial class, all of you. You will have today will be your lecture class, and during the week, starting next week, you will have one tutorial class as well of 1 hour. Check which tutorial section you belong to, go to that class, okay? Clear? Any questions, you can just you can text on Teams, or you can email me. If you want to have any consultation, write down to me 2 days earlier, okay?